we are proving this theorem that if is non-degenerate on W, okay, this is subspace of V, then V is W direct sum W perp. That's, I mean, we proved the other direction is easier. That is, if V is W direct sum W perp, then it follows that W intersect W perp is trivial, and therefore the form is degenerate on W. So now so that we did first, and this is what we are proving now. This is where I mean, it's the middle of the proof that I stopped. Okay. And so we first observed that since this is non-degenerate, W intersect W perp is trivial. Okay. So we need to show that V is W plus W perp. That every element of V can be written as something in W plus something in W perp. Okay. And by the earlier remark, be unique. The expression would be unique. So to this, what we did is that, so let W1 through WK be a basis of W. Extend it to a basis W1 through WK, Vk plus 1 through Vn of V. So with respect to, so let M, so I'm going to write this as a block matrix, some K by K block here, and then B, C, and D. This is N minus K, this is N minus K. Be the matrix that represents this form on with respect to this basis. Okay. Let's call it B. Okay. So now what we want is a basis in which the Vk plus 1 through Vn can be chosen, I mean, are chosen from W perp. Okay. So what we want is a basis B prime, which is the same W's and then some Vk plus 1 prime through Vn such of V such that V prime I is inside W perp, W perp for all for K plus 1 less than or equal to I less than N. That's what we want. Now let's just, so where I stopped is how would we, I mean, how would we know that we have found such a basis? In any such basis, in any such basis B prime, this form is given by the matrix. Okay. So the entries of the form are the some ith vector, I mean the the bilinear product of the ith vector in the basis with the jth vector in the basis. Okay? So the first part is the same, right? Because we have not changed w's. So there we would just get the same. Okay? Because we have taken the v primes to be orthogonal to the w's, we will get 0 here. And this is a symmetric or Hermitian form. So we will get 0 here. And we will get some d prime given by a matrix of the form of this form. Okay, this is k by k, and the d prime is as earlier. Okay, so this is what will be given. So we need to find such a basis. But of course, if you go and search for such a basis, is not easy. What we will do is a matrix manipulation, which will tantamount to finding such a basis. Okay. So note that. Okay, so let me call this matrix M prime. Okay. If such a B prime exists, B prime, where the second part comes from W perp, exists, okay. Okay. Then there exists an invertible matrix P such that M prime is P star M P. Right? This is just a change. I mean, change of basis from B to B prime will correspond to conversely, if such a P prime exists, sorry, I should not say recall. The recall was somewhere. Okay, so this is the end of recall. So now, so I'm continuing with the proof. Sorry, I should have said this. Continuing with the proof. Conversely, if such a P exists, I mean such a P exists, then there exists a basis B prime of the form W1 through WK, some V, okay, some V prime K plus 1 through V prime N with V prime I inside W perp. It is a 0 that signifies this anti-diagonal, I mean, not whatever anti-diagonal, this off diagonal zeros. I mean, this block 0 here and correspondingly block 0 here, because this matrix is Hermitian or symmetric. Okay, so this is the one that signifies that this 0 signifies that the elements V prime I are from W. Okay, because the zeros that you see here is just Wi against Vj, V prime j, and that is 0 is what is. Okay? So this is what, okay, with Wn for all. So this is the observation that we make. We are looking for a basis. Of course, it would not be easy to go and search for a basis and then construct it. Okay? So it is just, I mean, it is difficult. Much easier thing is to just manipulate the matrix, and remember the fact that manipulating the matrix like this, P star MP, corresponds to a change of basis. Okay? So this is all that we'll do. Okay? So that therefore we will show that such a P star P exists. Okay. Okay. So P will be some matrix. Again, so it is again convenient to write P also in the same block form, K by K and N minus K. Okay, so it is convenient to write. It will be because we're just
Hello, sir.
yeah, yes.
So, what do you mean by such a P? I mean,
A P
what kind of?
satisfying this condition. So when I
Oh,
say
okay,
such a
okay,
P, I mean a B prime satisfying this condition. When I say such a P satisfying this condition.
okay, okay, okay.
So sorry, maybe I should say. Okay, let me not erase this thing. Okay, let me just label this equation then. 1, and such a P means that is satisfying 1. Okay. Again, sorry, this again means satisfying 1. I mean, satisfying 1, again, that is also not very clear. What I meant is P star MP has these zeros. Okay. So it is convenient to write P also as some block form, because matrix multiplication will respect this sort of block. Again, this is K. I mean, this is K. This is N minus K, K and N minus K. Okay, and I mean, to simplify the calculations, so in other words, we are just thinking about I mean, whether the space can be we are sort of splitting the I mean, what the change of basis is depending on what it does to W and what it does to the remaining things. So, okay, so but for calculations, it is easier to do it. It is convenient to do it this way. In fact, we can even take P1 and P4 to be identity and P3 to be 0, and it would still work. Okay. So now let us take take P to be of the form this P1 is identity, P3 is 0, and P4 is identity, and here it's unspecified, where Q is yet to be determined.
Sir, could you just scroll up a bit?
Yeah, just let me finish the sentence. I will go. Yeah. I mean, it is convenient to write just to simplify calculations. Okay. But yeah. I mean, okay, but I'm saying we don't need to allow for all sorts of freedom in choosing P1, P2, P3, and P4. It will be very difficult to keep track of those calculations. It would be just sort of very long expressions. You can try to write it by hand, or you can use some. Yeah, actually, you can actually do this in Sage. I mean, the symbolic calculations using variables. But I haven't shown you. Maybe at some other time I'll show you. But I mean, I only showed you actual numerical calculations but the sort of symbolic manipulation also you can check in Sage. Various other things, not just. Okay, I'm saying if you try to write P star MP with all these degrees of freedom, it will be a very, very long expression. It's sort of difficult to keep track of everything. But I'm saying you don't need to worry about such a thing. We can take even nice looking matrix like this where Q has to be determined. Okay. So then what is P star? P star is just identity, Q star 0 and P. Then P star MP is P star MP is so this you can verify A in that block. Here we get AQ plus B. Here we would get Q star okay, sorry, I wrote in my notes Q star A plus C, but this I am not entirely sure. I not sure now. Actually, I'm little. This is what I meant. So please check. And here we would get. Sorry, what have I written? Here it's identity. P is like this. Its conjugate transpose will look like this. Okay. And here we would get something. It will depend on this Q and D and so on. Okay. So something which will depend on Q. Q, D, B, C. I think it depends on all of them. I have not written the expression down because it is not relevant. Okay. But because this will tell us what we have to take. Okay. So therefore, so we still have not found P. Yeah, we're trying to find a P. Okay. So therefore, take Q to be minus A inverse P. Note that A is invertible. Right? Because A did note that A is invertible. Since it represents the non-degenerate form on W. Okay. This A is what the degenerate form on W looks like. And but of course we cannot say. I mean, we can't say that the star here is what it looks like on W perp, because that will depend on whether this top right corner is 0 or not. So that's what we want to get. But at least on W we know that because this entries of A are exactly Wi comma Wj. I mean the product of Wi with Wj. So that we know. And okay. So then AQ to be this one. A is invertible since it represents the non-degenerate form on W. So therefore we can write. Okay. So if you take that way, then therefore then P star MP is A 0, and see M is Hermitian symmetric or Hermitian symmetric. Okay. So then this will also be automatically 0. That's why one needs to just check that this is the correct expression. Okay. Q star. Okay, so I'm a little concerned. I mean, I'm not entirely sure that this expression here is correct, but that is not really relevant. What you really need is that this top right corner is 0. Okay, and here we get some D prime. Some D prime. Okay, we don't care. I mean, it will be automatic that the bottom left corner is also 0, but that is not. I mean, one doesn't have to explicitly check that thing. And D prime will be something, and what exactly it is, we don't really need to worry. What we really need to worry is that the top right corner became 0, and that we have managed. So I hope. Any questions on this proof? Okay, so this proves. Actually, this proves one. Actually, just hold for a minute. I forgot how I stated the theorem. I just need to quickly look up my notes from last time. Just give me a minute. Yeah, that is how I had written. This was called part one of the theorem. Okay. And part two, so this proves part one. And part two, the statement was, just to recall, we need to show that, want to show that if the form is non-degenerate on V and W, then it is non-degenerate on W. So we'll use part one to show that. So since it is non-degenerate on V and on W, sorry, since it is non-degenerate on W, since it is non-degenerate on W, V is the direct sum of W with its orthogonal space. Okay, the thing that W perp by one. Okay. Now we have to show that we have to now use that it is non-degenerate on V and therefore also on W perp. So let M, and again I want to write the matrix like this: A, 0, 0, and some B.
Sir?
Yeah.
So what have you written there? WTST.
I want to show that.
Okay.
Is that what your confusion is? Okay, sorry. Want. See, when we write, we need to use these common phrases will be abbreviated. Various people have various abbreviations. Right? This, right? It is like writing QED at the end of the proof, or writing a box at the end of the proof to show it is ended. Yeah. So let M be this matrix. Let M be the matrix. So choose a basis. Sorry, you can't write a matrix without choosing a basis. Let W1 through WK be a basis of.
Hello, sir.
Yeah.
Sir, when we assumed K to be that of Q to be of that form minus A inverse B, then how did the Q star A plus C time?
That's what I am not. No. C is B star.
Oh,
but
okay,
I'm
okay,
worried
okay,
about.
okay.
Yeah. C is B star, but I'm worried about an A star now. But I mean, see, I didn't think through this very carefully at the proof because we don't need to know what. So if you do this manipulation, which will make the top right corner 0, then it will be automatic that the bottom left corner is also 0. Okay. So I did not actually check the calculation there. I wrote that this is what you get on the left, but I have a suspicion that it is slightly wrong.
Sir, but Q star A plus C is correct, I think. I mean,
Q, no, but A is.
Sir, A star is A, right?
A star is A. Correct. A star is A. Oh, sorry. I was getting confused between A star and A inverse. Okay, sorry. You're right. You're right. Then this is, thank you. Okay. So anyway, this is checked. Thank you. I mean, at that time I wrote this because this is what I got in when I calculated, but I didn't think through it that carefully to check whether this is correct. But yeah.
Be A conjugate.
Is what was it about?
A star be A conjugate because A is a matrix of an element. Something like that.
A star is correct. Wait, sorry. Okay, we will do that later. Okay. But the point is that, see, V is a real symmetric form or a complex Hermitian form, right? Therefore, with respect to any basis, the matrix will be Hermitian. So A star is A, or real symmetric. A transpose is A, right?
Yes. Okay.
Yeah. It will be. Okay. So therefore, A will be A star. As I said, I wrote the expression down, but without bothering to check because, as I said, I was just using blindly that if I can make the top right corner 0, the bottom left corner will automatically be 0. But yeah, okay, now that we have checked it, it's good. Okay. So now let us take a basis for W and some UN plus 1 through UK plus 1 through UN, a basis of W perp. Okay. Then V is the direct sum. So therefore, with respect to the basis of the union, the form is given by a matrix M, which is block diagonal, okay. This is what we just need to observe. Okay. The point is to choose a basis before we write it as a matrix. That's all. Okay. But the matrix will look like this, okay, because it is W perp and it's W direct sum W perp. Okay. So far, I've just used the setup of the previous part, which is that it is non-degenerate on W. Okay. Therefore, V is a direct sum. Now we will use the rest, which is that since the form is non-degenerate on V, M is invertible. So this we proved last time that form is non-degenerate on a space if and only if the matrix is invertible. Okay. In fact, if it's not invertible, then any element in the kernel, let's say the right kernel, will correspond to an element that is in the that is perpendicular to every other vector in. So this is M is invertible. So which implies that, of course, A and B are invertible. Okay. This, of course, we knew because this we knew. This is not a new information. We knew since the form is non-degenerate on W. That is what we started with. Okay. This is new information. And this implies that is non-degenerate on W perp. That, I mean, we are able to make this conclusion because it is in block diagonal form. Okay. I mean, if you take the product of Wi with Wj, okay, Wi with Uj, we will get 0. Okay, that is, so because it's in block diagonal form, we can make this. Oh, actually, probably not. All that we need is that the matrix is invertible, and from that we need to conclude that B is invertible. So this is the. So this proposition. This is the end of the whatever I call theorem. Okay, that's what I call it. Okay. So this is actually a sort of a crucial, I mean, an important state in the following sense. Okay. Given a vector space, and now that we have a form on it, okay, we would like to know whether we can decompose it into orthogonal parts, like the real space, let us say R2. The two standard vectors, basis vectors, are orthogonal to each other with respect to the usual notion of orthogonality, the dot product. Okay. So that is, so therefore we can rewrite it. We can rewrite R2 as the direct sum of the span of E1 with the span of E2, and these two spaces are orthogonal to each other. Similarly, in any Rn, we can do this. But so the key point is, when we say orthogonal, what is the form with respect to which we are discussing orthogonality? That is what we have. I mean, so far in school or in general, in many cases, we would just be thinking about the standard symmetric bilinear form, which is the dot product. Okay, that means the form that is associated to the identity matrix. That's what we would typically use. But whatever we do there, we can generalize into any other symmetric bilinear form. I'm just right now, as an example, I'm just discussing real space. Provided we change the notion of orthogonality to suit that form. So that is all that we have to keep in mind. So this theorem is sort of, I mean, gives us the sufficient and necessary condition. I mean, we will build this to decompose the vector space into a direct sum of orthogonal subspaces. Okay, so this is that's where we are going, and you should just think of this as sort of generalizing the usual notion that we can rewrite Rn, okay, as a direct sum of the span of the span of E1, direct sum span of E2, direct sum span of E3, and so on. Okay. Yeah. Okay. So this is where we are headed. So now, okay. So now at least we have found a sufficient and a necessary. We have found a useful criterion, or helpful. I should not say criterion. We have found something to look for. I mean, if you have to try to decompose a vector space into some W direct sum W perp, what should we look for inside in V or inside W, and whether we can do this repeatedly. Yes, that's what we want to. Okay. So so now, ideally, okay, so now let me write whatever I said. Let me just summarize and write. Okay. So we want, so given V and a form. So I'm being particularly ambiguous about the field, because if I'm discussing the field reals, I am discussing symmetric bilinear form. If we have a complex vector space, we're discussing a Hermitian form. Okay, so I'm just being ambiguous about that. Okay. We would like to know if there exists a basis say V1 through Vn, such that Vi is perpendicular to Vj for all I different from j. So if such a thing exists, then such a B exists, then V, then this thing. So let me just write R, maybe let me again be ambiguous. Span of V1 direct some span of V2 to span of Vn is a decomposition, is an orthogonal decomposition of V into one-dimensional subspaces. Sorry. Okay, so this is what we would like. The same thing that we know for Rn and the usual notion, the notion of, the definition of orthogonality using the usual dot product. We would like to now do this in general. Okay? Given a form, given a real or complex vector space, and a form, real, symmetric or complex Hermitian, as the cases, can we do this? This is what we would like to know. The previous proposition gives us a way to sort of break the problem down to smaller and smaller vector spaces. Okay? That we have to look for a subspace W on which it is non-degenerate. Okay? And then we will have to work with W perp. Okay? And for that, okay, so we need to use the other part. Okay? So this is how we will proceed. Okay, so first is a lemma which says that we can find a basis, we can find a W on which it is non-degenerate. Okay, in general, okay, lemma. If the form is not identically zero, then there exists a vector such that VV is not zero. Okay. So let me just remark here. So the span of V, W, let's call it W, is a subspace. We'll prove that. I just want to, how exactly we will use it, etc. We will prove it. But I just add a remark here: subspace on which this thing is non-zero, non-degenerate. Okay, so we can get V to be span of this V direct sum W perp by previous proposition. I think I called it a theorem. Okay. So this is, that's why we are looking for such a lemma. Okay. We can do this one vector at a time, and then so now we will have to ask the same question for W perp. What is the condition that we can do the same thing for W perp, and so on, and then okay. So that's what we would like. So that, we will prove that. Okay, but I just want to explain why we would look for such a lemma. Proof of lemma. Okay, so if the form is not identically zero, Identically zero means that there, I mean, okay, well, what I'm writing. There exist x and y in V such that xy is not zero. Okay, for some pair, the form evaluates to something non-zero. That's what it means. Okay, so we would like to replace x and y suitably so that the value of this form for that pair is real. So if it's already a real form, so if R is, if the field is C, or field is C, and this is a Hermitian form, okay, there exists C in C such that, in fact, non-zero, yeah, correct, like non-zero, okay, such that x cy is not zero. X cy, yeah, because I mean x cy is real, okay, and non-zero. That is because on the second factor, it is linear. So what we are doing is whatever this x comma y is, okay, call that thing C inverse, and then just multiply by C. Then you'll get one. I mean, could be any C, okay, but just want it real. But and of course, it'll be C is non-zero, x comma y, the product is non-zero. So therefore, the this whole thing is non-zero. Okay. So replace y by y by cy to assume that xy is real and not zero. So all that we are saying is, of course, we don't need to do this step if you're already working with real symmetric. I mean, if you're in the case of real vector spaces and real symmetric forms. Maybe just add that as a remark in this. No need to do this. If we are dealing with real vector spaces and real symmetric forms. Okay. This is required only if you're in the complex case. But the point is this is here. Okay. But okay, so therefore yx, which is just either if it's symmetric form, it is just xy. If it's Hermitian form, it's xy bar, but it's in real. So therefore, this is also equal to xy. I'm not talking about arbitrary x and y. There exists a pair with this property. Okay, that's what we have proved. Now write x plus y this is by linearity. This is just xx plus 2 times xy plus yy. That is just by linearity. Yeah. So now there are 3 terms in which the same vector appears. I mean, 3 terms in which it is the same vector appears in both positions. Okay. So there is so now what is the conclusion? Okay. So at least one of, so note that 2 times xy is not 0. Therefore, at least one of the remaining 3 vectors, x plus y, x plus y, xx, yy is non-zero, which is what we wanted to show. We wanted to show that there exists some vector v such that vv is non-zero. Because if all three of them are or these three are zero, then we'll get that 0 equals 2 times some non-zero number. Okay, so that cannot happen. So it's non-zero. Okay, so this is the proof that there is one vector v with this property. So now we will prove the theorem that I stated earlier, where we are headed, which is that let this be a symmetric or Hermitian, okay, form on V. Okay. This is over R or over C depends on the thing. So okay, remember these are two different hypotheses. Okay. We discuss symmetric forms when you're discussing real vector spaces, or we discuss Hermitian forms when you're discussing complex vectors. So let this be a Hermitian form. Then there exists an orthogonal basis of V. That is a basis V1 through Vn such that Vi is perpendicular to Vj for all I different from J. So this is okay. So we will prove. So we would like to use the previous lemma, which is that if we have a form that is not identically zero, then there is a vector whose product with itself is non-zero. So that's what we would like to use. But of course, we can do that only if we know that the form is it's not identically zero. So we need to rule out that case first. So case one, the form is identically zero. This implies that in every basis of V is an orthogonal basis. Because you take any basis, if I is different from J, Vj will be zero, because the form itself, doesn't matter what you put into the form, the result will be zero. So this is the first, okay, so this is the easy case. So we will, okay, but we need to get rid of this so that we can apply the previous lemma. Case two. Sorry, I should clarify. I should just a minute. Yeah, sorry. Proof is by induction on dimension. Induction on dimension. Okay. So we'll assume that all vector spaces of smaller dimension, the theorem is true for all vector spaces of smaller dimension. Okay. Yeah, so this case one, although does not use inductive step, but we need that to finish the proof, to start the induction before we get into case one. Okay. So by lemma, by the earlier lemma, so this is not identically zero. Then by the earlier lemma, there exists a V1 in V such that V1 is not zero. Okay. So then, so let W be with the span of V1. So then so what is this is given by maybe it's just writing it into the matrix. Okay. Note that the form is non-degenerate on W, since for all W prime inside W, for all W prime W minus 0, okay, W prime is a non-zero scalar multiple of V1, right? Because W is a scalar, non-zero scalar multiple of V1. W prime is a non-zero scalar multiple of V1. The first scalar you have to take it out in conjugate, and the other one you just take it out, and the product, that's a non-zero scalar, okay, and that times this product is what we want. Okay. So this is non-degenerate. Therefore, we can apply the previous lemma, previous theorem that we proved in. We started in the last class, finished the proof today. Okay. So therefore, V is the direct sum of W with its orthogonal complement, okay, by the earlier theorem. Okay. So now, so this is a direct sum, okay, and the matrix will look like the part for W, which is just a 1 by 1 matrix, and then part for W perp, okay, which is complementary dimension, okay, n minus 1. By induction on dimension, okay, W perp has an orthogonal basis. Okay, let us call it V2 through Vn. Then V1 through Vn is an orthogonal basis of, okay, because if you take any Vi I different from J, Vi comma Vj, if I is 1, then Vj is in W perp and they're orthogonal to each other. If I and J are both greater than or equal to 2, then by choice of them being orthogonal inside W perp, they will be orthogonal inside V also. So this is the theorem. Okay. So if we have, okay, so this is a, so this is a, this is a generalization of the fact that with respect to the usual dot product, or with the usual Hermitian standard Hermitian product, okay, this real vector space or the complex vector space, if you can decompose it into orthogonal basis, which is which is the standard basis form an orthogonal basis. They are all perpendicular to each other. So this is, okay, so this is a this is a generalization, and we have used various things that we have proved along the way.
Sir, could you just scroll up a bit?
Yeah. Sorry, how far up? This is fine?
Yes, sir, this is fine. Okay, sir, fine.
So in the next lecture, I will, I promised an example of some place where all of this thing is used. Okay, so I will do that in the next lecture, or maybe so there's still more to discuss about orthogonality. Maybe I will wait for one more lecture. Okay, so we are still sort of nowhere. I might need a little, or maybe I will do both next lecture. So I was thinking that I will finish this discussion about orthogonal stuff today, but I think in another 15 minutes I won't be able to do it. Okay. So I will do some little bit in the next lecture, and then show you an example where, where, I mean, outside this thing that we're discussing now, okay, where these ideas have to be used. Okay. It'll be some simple example in multivariable calculus. I agree. I understand that you may not have seen enough of multivariable calculus, but rigorously, because the course is just begun. I mean, it's going parallel, right? So but I actually, when you revisit this example after you understand, I mean, a little bit more of things will become more clear. But I agree that I mean, these topics are being discussed sort of with the motto that, okay, you learn it now, you will need it in the future. But I personally, I hate to teach something like this, but with that motto, so I will try to justify the existence of these things at least a little bit. Okay, so now, okay, this is. So now we discuss orthogonal projections. This is where I mean, I think you have seen these things at least in the last semester for real vector spaces. But yeah, so another thing again, of which I am no expert and I cannot speak with any degree of any authority, is that this idea of orthogonal projections is used in many other contexts. Okay? I mean, in many contexts where things have set up as solving large systems of linear equations. Okay? Lots of applications in data science, statistics, that sort of places, engineering, where you have to actually solve various systems of equations and sort of find the shortest length between two things, one subspace and one point, that sort of things. Okay, whatever we are discussing now is used. This Gram-Schmidt orthonormalizations, etc. I mean, some idea of that behind that will be used. Okay, so that's actually, so this is a topic that has actually somewhat concrete applications, except that none of those things can be easily discussed at this point, because you have not done the. I mean, there are sort of applications in sort of related areas of mathematics and not directly something that I can explain with the stuff that we have developed so far. So that okay. So, but I will try to at least some calculus examples I will try to do in next on Tuesday. Okay, so orthogonal projections. Okay. So suppose that is non-degenerate on V on W. Yeah, this is inside. Okay. Then V is W direct sum W perp. Okay. So for every V inside V, there exists a unique W inside W and W prime inside W perp, such that V is W plus W perp. Right? That's what we mean by it's a direct sum. Right? Yeah. Question, somebody? Okay. Okay. So now this map. Okay. So there is the map, okay, which takes this V to this W. Okay. It's denoted by pi from V to W. Okay. V goes to this W where W and W prime are the unique elements as above. Is called the orthogonal projection of V to W. And the point is that what one should keep in mind is that pi of v and v minus pi of v are orthogonal to each other. That's what is. Okay. Otherwise, with respect to any subspace, we can do this, right? I mean, if there is if there is any subspace W, okay, take a basis for W, extend it to a basis for V, okay, and then any element can be written uniquely with respect to that basis. Okay? I mean the new basis, and you pick out the part that came from W, and you can write. That is not the point. Okay, the point is that pi of V and V minus pi of V are orthogonal to each other. Okay? So that is okay. So I mean the picture that you should keep in mind is that this is an obvious picture. So okay, so there is some V here, okay, and let us say that this is V is R2. Okay, this is little v. W is the span of E1, and W perp is the span of E2. Okay, and this vector here is pi of V, and this vector here is V minus pi of V. Okay, and these are, I mean, the two red vectors colored in red are orthogonal to each other. Okay, this is what, and what was used is that it is non-degenerate on W. That is what is used. Okay, and okay, so this is okay. So such a thing is called an orthogonal projection. Okay, so we have used. I mean, this is not something that, I mean, we are using stuff that's related to orthogonality. Okay, it is not true that if you just do it for an arbitrary W, we would get this condition. The two components are orthogonal to each other. So, remark, if W is such that, is that said, this form is degenerate on W, we may not have such a projection. Okay. Because this is because so it is degenerate means that W is W perp. W intersect W perp non-trivially. Okay. So take V inside the intersection. Okay. So if there is an orthogonal projection and we took this V inside the orthogonal part, W perp, that will go to 0. Right? Maybe I should just add that here. Pi of V is V for all V inside W, and pi of V is 0 for all V inside W perp. These are all just consequences of this definition. So think about here, if you take a vector that is in the span of E2, its projection onto W will be 0. Okay. And if you take something that's already in W, its projection to W is itself. Okay. That's what, but okay. So then pi of V should be V. This is not 0. Since V is inside W, and pi of V should be 0 since V is inside W perp. Okay, and this is a contradiction. I mean, V is non-zero, but if such a pi existed, then we would get that V is 0. Okay, that's a contradiction. So this exists. That on the subspace, the form should be non-degenerate. Okay, it's a necessary condition for projection like this.
Sir?
Yeah.
So you've written we may not have such a projection, right?
Actually, what I guess. Huh? I just told that actually what I showed is there is no such projection. Yeah. I am not. Yes. The way I've written, I'm probably saying there's a likelihood statement, but I am not. I'm just saying that if such a projection existed, this is what you would get, right? So maybe I should say we will not have a projection. Is that what your confusion is?
Yes.
Correct. So correct.
Sir, when
yes.
we are talking about whether we will get such a projection or not, that is particularly on W, right? I mean, we won't
Correct.
get
It is
such
a
a projection on.
non-degeneracy of the form on W that is both necessary and sufficient.
Okay, sir. So we won't have any such projection on W, but other than that, in other subspaces we
Oh,
can
that
have
could
such.
be. Yeah.
Okay.
The form could be non-degenerate on some subspace and degenerate on some other subspace.
Yes, sir. Okay.
Yeah, it is always, I mean, the projection is onto the given subspace, and the question one has to ask is whether the form is non-degenerate on that thing.
Okay, sir.
Yeah. Okay. So So this is yeah. So maybe the next is this formula for projection, but I think maybe I'll just postpone it. I'll do it next time. I think I've already given enough stuff for one lecture. Just read this carefully. Make sure that you understand. Okay. If you don't, if you're not sure, try to work out some example. Even inside R2, try to use something different from the standard basis, or with respect to the dot product itself. Okay. Or take some V1, V2 different from the standard basis, but use the dot product. Then remove that condition also. Choose a different symmetric bilinear form and see. Even take one that is diagonal. Okay, then you can work with standard basis and see whether you can follow through the proofs. See, it is one thing to actually. This was one of the concerns that one of you wrote on the web. It is one thing to be able to follow a proof, check line by line, but it is another thing to, of course, have come up with. But let's not worry about it because these things have. The way the proof is written in a book is after much thought by the author and somebody who has lots of experience, etc. So let's not worry about that issue. But it is another thing to sort of understand what the proof is, how the proof proceeds. And what I would strongly recommend is to take a few examples and check step by step what is the proof doing in that example, and that would clarify why the proof is why the proof is as it is. Why are those steps being checked? Okay. And though my recommendation is just take even small examples and see if you understand what the proof is doing in that step. Okay. And step by step, look at what the proof is saying and see what it is doing in the specific example. And I think if you do 2-3 examples, right, of increasing difficulty as you go along, even 2 or 3 dimensions, you don't need to go. You probably won't need to go beyond R3 for these things. Okay. And then you should be able to, maybe R2 might be too easy for some steps, but all these orthogonal projections, forms, etc., you should be able to get a reasonably good intuition by looking at R3. Okay. R2 might be sometimes too simple. Okay. So please do that. So next lecture I will do the rest of the section, orthogonal projection formula, Gram-Schmidt, etc. And then I will do an example, which at least maybe in the next semester or so, you will develop ideas for that to understand how these are used. Okay, so I'll stop here.
Thank you, sir.
Thank you, sir.